That is actually a very dangerous prank. That very, very bad, dangerous prank flipping. So you know when you play Tetris, I'm pretty sure most people have played Tetris before. It's a really fun little game. It's been a long time since I played it, but it's really fun. So you've got these four four-piece tetrominoes, and there's a few of them that have like pairs with each other. So, example, there's one like shaped like an L, and one shaped like a backwards L. And sometimes you get one of them, and you want the other one. And no matter how you rotate it, you're stuck with this one how it is. And you just wish that you could just reach into the tetromino board, and you could just take it out and flip it around and put it back. But the game doesn't allow you to do that. The game just says all you can do in the game is rotate it around in the two-dimensional space you have. So the thing about these things is that means that you can have shapes that if you were allowed to flip them, put them back, they would be able to be different shapes entirely in this two-dimensional landscape. And there are many shapes that you could do this with. Similarly, in 3 dimensions, that is true as well. There are molecules that no matter how you rotate them, you cannot change them to another twin molecule that actually exists as well, that is like a mirrored version of it. And if you were able to take one of these molecules and take it out of 3D space into 4D space, flip it around, much like we flip that tetromino around, and put it back, you would get the other molecule. Now, sometimes these molecules, one version would be something in all the foods or something that you breathe, something healthy and fine, and the other one would be a deadly poison. And I'm not making that up. There are molecules that are actually like that. And imagine that's like the same in Flatland. So we're going to go to Flatland, we're going to take one of those people, we're going to lift them up like a pancake, we're going to put him back, and they'll see everything that's been reversed. Right will be left, left will be right. But the worst thing of all is that some things that were fine would become deadly poisons. So these like poisonous molecules, they like breathe in and they die pretty quickly. And not pretty quickly, they eat food, and food, basically all food would be poison, or a lot of it would be. And if you did that with 3D human, a 4D entity did that to a 3D human, flipped them around, put them back, well, it would be really bad, because I don't remember the specific names of these molecules, but they're really common, and because there's a lot of complex proteins and everything. And you'd eat food, and then a person would eat food, and then it would be like poisonous. Not to mention that everything to your right would seem like your left, and so everything would look crazy. It'd be like, imagine going to your house and seeing that like the room that was on the right is now on the left, and the one on the left is now on the right, and all the lettering, all the ink and everything, and like letters, everything printed is completely reversed, and everything is like reversed. So if something is not like this, where it doesn't have polarity, if something has polarity, it would be different. And like people would say the right hand is their left hand, stuff like that. Basically, like if you look into a mirror, if you imagine stepping into that mirror, universe in the mirror that it looks like, even though it's just a reflection, if it actually was one, that would be similar to what would happen if you got flipped. And so that's really dangerous. So it sounds like a funny prank, but it could go very wrong. Alright, so why don't we talk about curvature of space? So space. So by now we can understand that space is 3-dimensional. That means it's flat. That means it could be a surface of something, because 4-dimensional objects have 3D surfaces. So what if space is the surface of a hypersphere that is really big that we can't tell it's curved? Now let's imagine flatlanders on a sphere. Or how about, instead of flatlanders for a change, how about a 3-dimensional animal? How about an ant, a really small ant? That would live on a balloon, live on this big balloon, and they might think it's a bit curved, because they notice that they can't see others once they go below the horizon. They'd all live on this like balloon or something. And so they could measure the curvature by drawing a triangle, and if the angles didn't add up to 180 degrees, that means that there's curvature in the triangle, and also in the space, the flat landscape they're living on. And so so you might think there's no way for us to understand that based on what we're already living with, because this universe curve would be so slight we wouldn't be able to tell it's there. But there actually is something similar, scaled one dimension down, the Earth. The Earth is a sphere with a 2-dimensional surface. It seems like a flat surface. It seems like just a regular flat surface, but it actually isn't. If you measure a triangle big enough, you can actually calculate by the angles that's curved. So what you could take your friend to a field or something, and you could like draw a big triangle and measure the angles, and you would get 180 degrees because the field would be flat, and the Earth would appear to be flat on that scale. But just because that you got 180 degrees with this triangle's angles added up does not mean that the Earth is flat. It means that the Earth is either flat or it's very, very huge, so huge that you cannot measure the curvature with the level of technology precision you have, or that you have to measure from a bigger area. If, however, you use a really big triangle, one that's thousands of kilometers in scale, or even hundreds of kilometers, you could calculate that there is a curvature of the Earth. The angles would add up to more than 180 degrees. You can even try that with the tennis ball. Draw a triangle like a nice straight line, then another one connecting back to the first. Measure the angles with the protractor. They'll be more than 180 degrees, so it's pretty cool. So what if you want to do that for the universe? Well, for the universe, instead of being... So of course for the Earth, we're three-dimensional, but we live on like a two-dimensional surface. On the universe, it would be a three-dimensional surface of a four-dimensional hypersphere. Again, all points would be equidistant from the center, which would be outside of our universe. Here we would not be on the surface of the universe, much like we're on the surface of Earth. We would be like part of the surface of the universe because everything would be inside. Just like you could imagine a sphere with tiny flatlanders on it, and they would be like inside of the surface, and the actual center of the sphere would not be like within their space. They would only be able to be on the surface. So we'd be like that with this four-dimensional hypersphere, and we'd be on the surface of it. And it would be expanding. That's also how a lot of physicists think the Big Bang happened. When they say it happened everywhere, that doesn't make sense. But if you imagine it was infinitely small and it grew like this, and of course when I imagine these spheres, this is actually scaled down one dimension. It would actually be four-dimensional. But so all points in space would have eventually, if you go back far enough, would have been at this one particular point. All right.